Hello! Welcome to Essay Nights, the Essay Slayers. My name is Julie and I will be your instructor as we read through Developing Embedded Electronic Technology. The article source is embedded in the video description below. Feel free to read along. Please note that you can get a custom, plagiarism-free essay for as little as $10 a page at Essay Nights. The link is in the description. Over the past decade, increased functionality and reduction in size are important factors in developing embedded electronic technology. As a result, small but powerful handheld devices such as music players, mobile phones, wireless sensors, etc. are available in the market. The size of these devices is further reduced that instead of portable devices they are becoming wearable devices. At present, these devices are powered by using batteries with finite power supply. Once this power is finished, batteries needs to be replaced, which is tedious and expensive when devices placed in remote locations. Research advances in the field of low-power electronics, wireless technology and sensors to operate continuously has led to increasing demand of self-powered electronics. One possible technique to potentially alleviate these issues is harvesting energy from surrounding environment to power electronic devices. Energy harvesting, or power scavenging, refers to capture the energy from environment or energy surrounding a system or other energy sources and convert it into usable energy for electronic devices. Harvesting energy from environment is a promising alternative to reduce system mass and volume, increase functioning and reduce maintenance cost. The attained electrical energy from kinetic energy, electromagnetic energy and thermal energy is used to develop electronic devices that can be recharged using a secondary battery or to power electronic devices directly. The main objective of this project is to discuss and investigate on various methods of energy harvesting technologies. This paper presents a detailed study on piezoelectric power generators, PEG. Energy conversion using piezoelectric power generators, PEG, is more advantageous as they can be fitted comfortably in small micro-electromechanical systems. PEGs can work continuously for an infinitely long period of time, if the force applied and the temperature outside are within the range of the system. Piezoelectric technology has gained a lot of interest in the recent years due to the advancement in the development of low-power electronic devices and portable devices. In order to meet the weight and power generation requirements to these devices, design issues and electromechanical characteristics of piezoelectric materials should be studied. This paper also presents previous works done on piezoelectric energy harvesting techniques, a detailed study on modeling and design issues, their stability and power generation. Chapter 2, Background Technologies. The two major technologies must be considered when developing energy harvesting electronic devices with less weight, low power consumption and reduced maintenance cost. Two technologies play an important role to overcome these issues. 2.1 Battery evolution. The technological advancement has led to decrease in the size, weight and increase in performance and also to recharge batteries. Energy necessary for majority of portable devices like music players, cellular phones, digital cameras act as provided by batteries. Batteries act as a storage place of energy, also called as reservoir energy source. Batteries can be characterized by calculating their energy density, self-discharge and life cycle. Energy density is classified with respect to volume and weight, also called as volumetric energy density and gravimetric energy density. Below Table 1 discusses typical values of energy density, self-discharge and number of cycles of available commercial batteries. A vast research is on its way to further reduce the size and increase the performance of batteries, which in turn directly affects portable electronic devices. Different types of battery technologies like thin-film lithium-ion or lithium polymer cells, power generation using fuel cells, methanol or hydrogen, NiCd or NiMH batteries are available commercially, which has limited lifetime and needs to be refueled alternatively. The concept of secondary battery plays better role for portable or ubiquitous electronic systems, because these batteries can be recharged or refueled in many number of ways without removing the battery from the device. One such possibility is through capturing energy available in the environment, also called energy harvesting. 2.2 Power consumption. The trend in integrated circuit technology resulted in shrinking the size of transistor, which in turn resulted in reduced supply voltage, VDD. Due to advancement in low-power electronics, electronic devices are manufactured with different modes, inactive, sleep mode and active mode, to save the energy. As a result, a discontinuous operation method is used to manage between these modes to refill the energy storage reservoir during inactive or sleep modes using energy harvesting technology. The model of the device and power consumption factors is explained. Maximum performance of the device reduces the time per cycle to give higher number of cycles, or services, which results in increased energy consumption from the battery. Maintaining same number of cycles, or services, reduces the time per service, which results in constant power supply from the device. Chapter 3. Energy harvesting devices. Energy harvesting devices capture the untapped abundant energy available in the environment and convert different forms of captured energy into electrical energy to power electronic devices. Energy harvesting devices are broadly classified into two types: 3.1 human energy devices, 3.2 environment energy devices. 3.1 human energy devices. Energy is generated by humans in different forms. Movement, heat, vibration, is captured using various devices attached to human body. The amount of energy captured from human body is very small. Human energy devices are divided into two types. First is human active energy and the other one is human passive energy. Human active energy devices basically work on the principle of increasing the ratio of time of use with respect to time of charge. These energy sources are controllable as they provide harvested energy when required. Devices such as radio receivers, electric torches and mobile phone batteries are powered by using only human energy by winding a hand crank, finger motion, paddling, by shaking the device, and walking. All these movements come under kinetic energy. Human active energy finds its application mainly in industrial area. One example where human active energy can be implemented effectively is remote control. The device is powered by applying the mechanical force to push the switch which bends the cantilever piezoelectric ceramic. Another example of human active energy is scavenging energy with shoe-mounted piezoelectrics, where energy is extracted while walking helped to power RFID tag system. 3.1.2 Human passive energy. Human passive energy concept is mainly applicable to portable and wearable electronic devices. These energy sources cannot be controlled. Energy is harvested only whenever it is available from sources such as blood pressure, body heat, etc. Basic wearable devices to implement human passive energy are wristwatches as they have very low power consumption. Wristwatches can be powered by using both kinetic and thermal energy. Wristwatches powered with kinetic energy have power output of 5 microW in normal condition and 1 megawatt when forcibly shaken. Wristwatches powered with thermal energy have power output of 1.5 microW when the temperature difference is 1 to 3 Celsius. Human passive energy concept is also implemented in several other applications such as attackable medical devices, self-powered heat sensors and mobile electronics. 3.2 Environment energy devices. Severe approach and research is going on from the past few decades on to capture surplus ambient energy available in the environment and various sources like solar energy, wind energy, RF, etc. The energy required for low-power electronic is in the order of hundreds of microwatts. Extracting energy from environmental energy sources is explained in Chapter 4. Chapter 4. Electromagnetic radiation. Electromagnetic radiation is an important form of energy source available abundantly in the environment in the form of solar energy, RF energy, etc. 4.1 Solar energy harvesting. Solar energy is available abundantly in the environment surrounding us. However, in designing an efficient and mature technology to harvest this solar energy, requires an in-depth analysis of several factors. Availability of solar energy is highly time-varying, mostly depends on sunlight, weather in location, latitudes and longitudes. As a result, storage elements like batteries and capacitors are required to harvest energy. The storage components altogether must work simultaneously in different characteristics, voltage and current, to achieve maximum efficiency. Among various methods of modalities available, solar energy harvesting through photovoltaic system provides highest power density 10. The average lifetime of photovoltaic cells is around 20 years. The main source of energy for photovoltaic systems is solar radiation. Photovoltaic systems are found from megawatt to the milliwatt range, producing energy from a wide range of applications like grid-connected PV systems and wristwatches. Various factors like inclination angle and orientation of photovoltaic cells affect the amount of solar radiation on solar cells outdoors. Indoor irradiances widely vary in the range of 3.5 to 20 watts per meter squared, as the solar cells are made of semiconductor materials. The power conversion efficiency of photovoltaic solar cell is defined as a ratio between the solar cell output power and the solar power impinging the solar cell surface. 7. Photovoltaic solar cells technology is implemented in radios, solar lanterns, wristwatches, battery chargers, etc. This paper discusses the design issues of harvesting, battery issues, implementation and power management. This paper also explains helium-mode and Prometheus architectures and their design, implementation and performance evaluation. 4.1.1 Storage technology and cell characteristics. Due to uncertainty in the climatic conditions, energy storage plays an important role in storing the available harvested energy using energy storage mechanism. There are two available technologies in storing harvested solar energy: ultracapacitors, also known as electromechanical double-layer capacitors, and batteries. 7. Batteries have very high energy density when compared with ultracapacitors, whereas ultracapacitors have very high power density when compared with batteries. Different types of batteries are available commercially in the market. Among them, 4 of them are commonly used for storing the energy. 1. Nickel metal hydride, NiMH, lithium-based, Li+, nickel cadmium, NiCd, sealed lead acid, SLA. Among the 4, NiMH and lithium-based batteries are commonly used and are more efficient, whereas sealed lead acid and nickel cadmium are rarely used because of relatively low energy density and temporary capacity loss caused by shallow discharge cycles. Lithium-based batteries are more efficient with longer lifetime and are used vastly among the 4 technologies available, even though they are more expensive. Solar cell characteristics vary vastly from battery characteristics. Solar cells are arranged in series and parallel combination to form a solar panel, which are characterized by open circuit voltage, VOC, and short circuit current, ISC, parameters. Solar panel acts as a voltage-limited current source with optimal operating point. Power extracted from panel is maximized. Figure 2 shows VI characteristics of 4-4.0-100 solar panel where VOC and ISC acts as X and Y intercepts simultaneously. 10, 19. Observing the figure 2 clearly show that the value of the short circuit current decreases as the incident solar radiation decreases and vice versa, whereas open circuit voltage remains constant. 4.1.2 Circuit design and power management. The most important step in achieving an efficient solar energy harvester is to design a harvesting circuit that can manage energy drawn from solar panels and effectively transfer the captured power to the target systems. However, while designing a circuit, the concept of maximal power output should be considered. In order to overcome this problem, Maximal Power Point Tracker, MPPT, is used continuously to track the optimal operating point and also by clamping the output terminals of the solar panel to fixed voltage. 18. Adding to this MPPT, depending upon the operating voltage and supply voltage required, a DC-DC converter is used to continuously supply voltage to low-power electronic systems. In all, the first and foremost target of any solar energy harvesting circuit is to capture all the harvested energy from solar panel and effectively utilize the total power, even megawatt of power. Power management is another important aspect in solar energy harvesting design other than circuit design. The concept behind the power management technique is distributing energy to sensor networks instead of minimizing the total energy consumption. An efficient power management system should satisfy all the conditions like the information about availability of energy for future use obtained by developing parameterized macro models for power source and routing of solar power to more than one node. 4.1.3 Helium-mode design. The word helium-mode had its origin from a Greek word helios, which means sun. By understanding the name, we can say that this system is powered continuously by solar radiation. Helium-mode system is built using MICA2 platform with single storage energy scavenging system. This system is designed to be user-friendly where the user can simply plug in the HelioMote system, consisting of solar panel, batteries etc. to the target system for its function. While designing a HelioMote harvesting system, several factors like hardware, software and performance of system should be considered. HelioMote system uses a solar panel with an area of 4-4.0-100 with open circuit voltage of 4.0 V and short circuit current of 100 MA. The values vary slightly depending on time of the day. The power captured from solar panels is used to recharge two AA-sized 9AH batteries, each with a capacity of 1800 mAh. The voltage of the batteries varies between 2.2 V and 2.8 V. The amount to which batteries should be recharged is monitored to a particular operating point, called maximal power point, as overcharging is hazardous and also causes instability to battery's performance. Similarly, undercharging of NIMH battery leads to the damage of rechargeable batteries as the load continues to draw power from batteries even after the voltage has dropped below threshold. In order to overcome this problem, a threshold voltage is created. Electronic systems should be provided with continuously supply of power for its proper functioning. In order to provide a constant supply of voltage, specific DC-DC converter is used depending on the system supply voltage and operating voltage range of the batteries used. Also, a boost converter is used to improve power supply if the supply voltage falls below the battery voltage. The amount of harvested solar energy available and its usage should be monitored continuously. This can be done by Energy Monitor component. Information gathered from Energy Monitor is used to perform harvesting or performance applications in microcontroller. Careful steps should be taken while designing a PCB, printed circuit board, of HelioMote system. Electromagnetic interference, EMI, radiated from switching supply source should be decoupled by placing the ground plane low in the stack, which helps in preventing EMI affecting other circuits. 10. Small filter components are used when PWM, pulse width modulation, frequency of DC-DC converts value is above the operating frequency. Due to effective filtering of P currents, the noise frequencies fall drastically into filter stop bands. Noise can be reduced by placing the EMI components away from the RF circuits. Performance evaluation, or efficiency, of HelioMote system is tested by connecting a potentiometer in the place of load in order to vary load current. The efficiency of DC-DC converter is estimated to be 90%, however the total efficiency of HelioMote system is reduced to 80% and 84% for typical operating values due to reduction in the efficiency of filters, overcharge and undercharge protection units, diodes, board and battery monitor IC10. A complete mathematical analysis of HelioMote is presented in 24. 4.1.4 Prometheus System. Prometheus scavenging system uses double storage energy technology built on a Talos B platform for harvesting solar energy. 25. Harvested energy is stored in two buffers, primary and secondary buffer. Initially, primary buffer charged by available solar energy is used to power Prometheus node. The remaining extra energy available from primary buffer is used to charge secondary buffer. However, a shift of node from primary buffer to secondary buffers occurs when the primary buffer energy falls below threshold level. Node returns back to primary buffer until it is completely recharged. Prometheus energy harvesting architecture shown in the figure above has the following components like solar energy source, primary buffer, supercapacitor, secondary buffer, Li-ion battery, power switch enclosed to Talos sensor node and charge controller. Supercapacitor is used to power the node whenever solar energy is available. However, Li-ion battery comes into use only when there is no solar energy, that is during nights, on cloudy days, etc. So, supercapacitors are used as first storage component, whereas second storage consists of Li-ion battery. Prometheus harvesting system differs from HelioMote harvesting system with an additional storage component. Also, charging control is accomplished in software. A software driver is used to manage the switching of node between both energy storage buffers during charging to power Talos. The concept of two storage elements is implemented in Prometheus energy systems because the battery technology used in HelioMote has a limited number of deep recharge cycles. A model state diagram is shown below, which explains the logic implemented by the driver to switch between power sources. The main function of switch block shown in the above figure is used to switch between supercapacitor and Li-ion battery. By observing the state diagram and figure, we can state that a high threshold is created to draw a barrier between supercapacitor and Li-ion battery. Supercapacitor is used to charge the battery as long as the charge is above the threshold point when compared with Li-ion battery. As a result, battery is charged from supercapacitor. Whereas the supercapacitor is charged, recharge option is available when the charge is below the threshold point, that is, recharge opportunity is available. Node is powered by Li-ion battery when the recharge opportunity is not available. The node switches returns back to the supercapacitor when recharge option is available back again. The process repeats continuously depending on the availability of solar power. 4.2 RF energy harvesting. Radio frequency identification is a new technology developed to harvest energy from the potential RF sources like TV stations, radio stations, mobile telephony, wireless networks. Rectifying antenna, rectenna, is used to collect all the radiated energy and convert into useful energy with the help of Schottky diode located between the antenna dipoles. Rapid growth in RFID, radio frequency identification, systems has led increased applications in public transportation, logistics, airline baggage tracking, locate and track people, assets, etc. A radio frequency identification system generally consists of readers, or interrogators, and a number of transponders, or tags. Rectenna, receiving antenna, are used to collect the time-varying electromagnetic RF wave transmitted by reader to power RFID tag. There are two different types of tags in general. One is active tag and the other one is passive tag. Active tags are used in long-distance applications. Active tags are provided with their own battery supply, so their functioning doesn't depend on external RF energy. Passive tags transponders uses RF energy transmitted to power its functioning and lower frequencies within shorter a range. As passive tags don't include battery, they are cheaper and perform to greater longevity when compared to active tags. A typical RF energy harvester is shown in the figure below. Energy harvesting devices must have an energy receiver or antenna to collect the transmitted RF power by source. The area of receiving antenna is called effective area. RF signal is also called carrier signal. This signal, when passed through an antenna coil located on RFID tag, generates AC voltage across the coil. The effect of mutual inductance in loop antennas results in magnetic coupling between RFID tag and RFID reader. The amount of power generated depends on the effect of mutual inductance between reader and tag. This effect is shown in the figure below. The amount of power received from the antenna can be calculated as PR equals S if M2, if equals G2, PR equals picosecond by gram 1 G2, PR equals received power, PS equals transmitted power, if equals effective antenna area, G equals antenna gain, R equals distance. The RFID tag modulates and changes the amplitude of the received carrier signal. The reflected RF signals transmitted by RFID reader give details of changes in amplitude to denote the presence of RFID tag. A high Q crystal resonator is used for impedance transformation. The sensitivity and operational distance frequency are -30 dBm and 24 MHz respectively. The key benefits of RF energy harvesting are power over distance, when sourced to many receivers, and power is controllable. RF energy harvesting can be practically implemented in building automation in areas like indoor sensors, low light areas, behind walls and above ceiling. Other application examples are industrial monitoring and location tracking. But at present the amount of energy levels actually are too low that no electronic device is able to use them. Future advancement of harvesting technologies allows the development of low-power devices to recycle the RF energy emitted from different sources. Chapter 5. Kinetic energy. Kinetic energy is one of the most promising sources of energy available in our day-to-day life. The main principle behind generating kinetic energy is the mechanical deformation of a structure or some stress or strain applied on the structure or displacement of a moving part inside energy harvesting device. All these actions can be converted to electrical energy. Kinetic energy is available from both human and environment energy harvesting devices. Energy can be harvested using kinetic energy principle using three methods: 5.1 Piezoelectric energy harvesting. 5.2 Electrostatic energy harvesting. 5.3 Harvesting energy by magnetic induction. Two types of conversion technologies are used to harvest energy. One possible approach is to respond to vibration or displacement of a proof mass. The energy obtained by this process is dependent on mass. Another possible solution is the stress applied from an external element causes a deformation, elastic energy, which is converted into electric energy. 5.1 Piezoelectric energy harvesting. Piezoelectric energy can be generated by causing a deformation or applying a stress by different means to a piezoelectric element is directly converted to electric energy via piezoelectric effect. Piezo means pressure. Piezoelectric effect was discovered in 1880 by Jacques and Pierre Curie. Many sources like vibration of machines, structural strains, human motion, etc. are harnessed to collect piezoelectric energy. Piezoelectric energy generators, PEGs, are not complex systems and can easily be fitted in any closed material with no rotating shafts to generate energy. Two types of piezoelectric materials are used to convert mechanical force to electrical energy. 5.1.1 Piezoelectric films. 5.1.2 Piezoelectric ceramic. 5.1.1 Piezoelectric films. The first type of piezoelectric material, that is piezoelectric films, are flexible and exhibit piezoelectric effect due to the intertwined long chain molecules attracting and repelling each other. An example of piezoelectric films is a polyvinylidene fluoride, PVDF. PVDF exhibits stability over time and does not depolarize. PVDF material, when stretched or bent, produces an electric potential. When bent, the external part of PVDF sheet is expanded, whereas the internal surface of the sheet is contracted. The result of both these actions produces voltages across terminals. The expansion and contraction effect is shown in the figure below. 5.1.2 Piezoelectric ceramic. On the other hand, the second type of piezoelectric material is piezoelectric ceramic. The rigid and crystal structure of piezoelectric ceramic is responsible for piezoelectric effect. An example of piezoelectric ceramic is lead zirconate titanate, PZT. The expansion and contraction of PZT sheet. Two PZT unimorph sheet attached on either side of the metal backplate form a PZT dimorph, develops charge similarly as PVDF. Due to ceramic nature of PZT, it is not flexible as compared to PVDF. PZT unimorph using a metal backplate used to prevent damage is shown in figure below. The efficiency of piezoelectric energy harvesting device depends on several factors like piezoelectric material, circuit design, storage methods, type of batteries used, etc. Piezoelectric material and interface circuit design are identified as two main parts of harvesting device. The energy harvested from piezoelectric energy harvesting device is stored from future use using available storage methods. Rechargeable batteries and supercapacitors, ultracapacitors, are the two available technologies for energy storage. Rechargeable batteries such as NiCd-NiMn have different characteristics with a limited capacity of charging and discharging. To overcome this problem, supercapacitors are used as storage buffers. Supercapacitors act as resistive loads. The above gives an example of piezoelectric harvesting system. An interface circuit consisting of load or storage buffer with a rectifier is connected to piezoelectric material to convert energy. The interface circuit acts as a AC/DC converter. The concept of piezoelectric energy harvesting is practically implemented in industrial sector, transportation, human applications and structural applications. An example of practical implementation is shoe-powered RF tag system. The energy required to transmit 12 bits of wireless information through RFID tag is generated when the bearer walks with shoe. Another example is self-powered push-button controller, where energy is generated with the push motion of the button. When the button is pushed, the pressure is applied on PZT element, oscillates at a particular resonant frequency. Generated electrical energy is stored in a capacitor. All the above systems mentioned convert mechanical energy into electrical energy. A vast research is to be done to harvest energy from human movements for long-standing power supply to the electronic devices. Integrating piezoelectric systems with wireless sensor networks is another area where research focus is to keep for future advancement. A detailed study on piezoelectric energy generators is carried on in the Chapter 7. 5.2 Electrostatic Energy Harvesting. Electrostatic energy harvesting system principle mainly depends on the mature MEMS, microelectromechanical systems, processes. The key principle behind generation of electrostatic energy is that the moving part of the transducer moves against an electrical field. When the plates are separated at constant charge with the charge between two electrodes increases the volume of the electric field results in the increased electric potential energy. Different designs are developed to harvest energy. One among them is Coulomb-damped resonant generators, CDRGs, which is based on electrostatic damping. In CDRGs, parallel capacitor is operated with a constant charge and a cone capacitor operated with a constant voltage. Voltage, charge and capacitance of CDSGs is interrelated. Voltage will increase and capacitance will decrease if the charge on the capacitor is maintained constant, whereas both charge and capacitance decreases if the voltage on the capacitor is maintained constant. A model design of electrostatic energy harvester is shown below. An equivalent circuit diagram of the above harvesting model is shown below. By observing the circuit diagram, capacitance C is in series with voltage source V. The design discussed is often referred to as in plane overlap converter, as the transduction is quite insensitive to stray capacitances between the proof mass and package. At the initial point of starting energy harvesting cycle, the capacitor must be previously charged to a maximum capacitance point. Two different harvesting schemes are discussed in this paper. One of them is charge-constrained harvesting, in which charge is maintained constantly by open-circuiting a capacitor as its plate separated in response to vibrations. The conversion cycle moves from point A to B when the system capacitance is maximum max. MEMS capacitor is charged by an voltage source to an initial voltage, VSTART, which is less than maximum voltage, VMAX. The relation between both voltage and capacitor is squared rather than linear. The area BD shown in the below figure explains the shift of plates from maximum capacitance to minimum capacitance with constant charge Co. Voltage increases as the charge is maintained constant and the capacitor value decreased, results in the charge return back to dA. The process results in the output energy equal to area ABD. The energy gained from charge-constrained conversion cycle is less when compared to voltage-constrained conversion cycle. One way to overcome this defect is to add a capacitor in parallel with a MEMS capacitor. One of the main disadvantages in adding a capacitor in parallel is to increase the value of initial voltage source. Another type of conversion technique discussed is voltage-constrained conversion cycle. The conversion cycle starts when the capacitance reaches a maximum point with voltage source charging the MEMS capacitor, moving the cycle from AC, as shown in the above figure. The process of plates moving from Cmax to Cmin is shown using the path CD. Capacitor is discharged when the capacitance is decreased and parallel plate distance increases. This process is explained in the above diagram with the path DA. In order to move the plates, some sort of energy is required. We consider this energy as mechanical energy. The harvested energy during this process is either stored in a capacitor or a rechargeable battery. Path CD shows the mechanical vibration during the harvesting process. Path is used as a common path for both voltage-constrained conversion cycle and charge-constrained conversion cycle to transfer the gained energy from MEMS capacitor along the path. A constant voltage is maintained across the plates to convert mechanical vibrations into electrical energy. Greater amount of energy can be harvested if the voltage across the capacitor is constrained rather than charge across the capacitor. In order to achieve better efficiency results, the operation of switches should be done effectively. More care must be taken to synchronize the operation of switches with the mechanical oscillation, as the frequency of the mechanical operation depends on the resonance frequency of the mechanical structure. The frequencies are operated in the order of kHz for miniature components. 5.3 Electromagnetic induction. Electromagnetic induction is the process of converting the available ambient kinetic energy into electric energy. Electric current is generated by the relative movements of magnet and coil or due to changes in the magnetic field. The variation of magnetic flux across the electric circuit causes electric field. The coil typically acts as a conductor is placed within the magnetic field. The amount of electric current generated mostly depends on several factors like strength of magnetic field, number of turns of the coil, magnetic flux density of magnets, excitation frequency, geometric configuration and relative motion. Electromagnetic induction was first discovered by Faraday in 1831. Faraday's law states that a time-varying magnetic field incident normal to the surface of a coil will produce a voltage proportional to the number of coils, N, the area of the coils, A, the velocity of the spatially varying magnetic field, 2 picofarads, and magnitude of the time-varying magnetic field, BO. Both the equations given below explain the Faraday's concept clearly. The amount of electricity generated depends on the size of the coil. This shows that the big transducers with large area coils generate more energy than the one with small transducers with small area coil. Initially, this paper discusses a basic model of magnetic induction transducer. This model works on basic principle. The vibrations created in the generator affects the seismic mass, M, connected to a spring, K, move through a constant magnetic field to oscillate and out of phase with respect to housing to create a relative displacement. This displacement created is assumed to be in sinusoidal form, so that magnetic induction generator is able to convert into electrical energy. During the conversion process of energy from mechanical to electrical energy, electromechanical force, Phi, in transducer damps the mass movement of the magnet with a factor Bm. Basic model of magnetic induction transducer is shown below. The movement of mass, m, creates a displacement, z, t. L and Rc shown in the above figure corresponds to inductance and parasitic resistance of the coil respectively, whereas L and R corresponds to length of coil and load resistance respectively. Relation between electromechanical force and voltage is given by the following equation given below. Newton's second law of motion is applied to obtain transfer function. This paper also discusses two types of electromagnetic induction systems usually implemented in market. 5.3.1 Magnet through coil induction, 5.3.2 Magnet across coil induction, 5.3.1 Magnet through coil. The basic principle in a magnet through a coil induction system is, a magnet is translating through a coil with no relative rotation. The system consists of cylindrical coil of N turns of wire with a length Lc and inner and outer diameter of max and min respectively. Bar magnet used in this system is of length Lm, with radius Rm. The power generated using this system is low as the coil never experiences complete flux reversal. The average radius of the coil and the cross-sectional area is calculated as Rc equals AC equals PRC2, and the average diameter DC is 2Rc. When placed in a coordinate axis, the midpoint is placed at origin with longitudinal axis of the magnet fixed along the y-axis. The main advantage of this type of system is that it is easy to build. 5.3.2 Magnet across coil induction. In magnet across coil induction system, the magnet is moved across coil, generates high voltage as the coil experiences complete flux reversal. The system consists of a layer of magnets with air gap in between the magnets. Voltage is generated across the coil, as the movement of the magnet across the coil causes a change in the magnetic flux. Development of this type of systems is complicated to build. Chapter 6. Thermal energy harvesting. Thermoelectric energy harvesting is one class of energy harvesting system which converts thermal energy directly into electrical energy. Thermal energy is abundantly available in the environment in different forms or sources like human body, animals, machines and natural resources. Seebeck in 1821 discovered Seebeck effect which is implemented in thermoelectronics. Seebeck devices produce a relatively low voltage output in the presence of small thermal gradient Uchihara. Due to small thermal gradient, the power output and efficiency of the devices is low. To overcome this problem, researches are conducted to develop superlattice structures. The design of a thermoelectric generator is basically done by sandwiching thermopiles between hot and a cold plate. Thermocouples basically made of P-type and N-type of semiconductor connected electrically in series and thermally in parallel when arranged in large number from a thermopile. Seebeck coefficient is positive for p-type materials and negative for n-type materials. An electric circuit is formed by connecting a load connecting to electricity. An efficient system with maximum power can be generated only when both the load matches electrical resistance of system and thermal conductance of the thermocouples equals that of the air between plates. Volers. Temperature gradient at the junction and Peltier effect are the two factors affecting the transmission of heat in thermoelectric systems. Converting ambient thermal energy into electrical energy using Seebeck effect can be fundamentally explained in the following discussion. An electric potential difference is created when two conductive materials, A and B, attached to a load, L. Two temperatures T1 and T2 are taken to form a temperature difference T2 T1. A charge, G, flows across the resistive load when a temperature difference, T2 T1, is applied across the conductive materials. Equation governing the Seebeck effect is taken into consideration. B. N equals although G rab equals total resistance of isothermal loop measured in ohms. Although equals open circuit voltage. G equals induced current flowing through load measured in amperes. The above equation describes the electric potential difference in volts across load. ABO equals P AB 1/T dt. ABO is a function of Peltier coefficient, P AB. Peltier coefficient is different for different materials and is measured in joules per coulomb Kelvin, J/CK. Thermoelectric energy generator is implemented in many practical areas like human body, machines and natural resources, etc. Seismothermic wristwatch is one example of system implemented to human body. Thermic wristwatch uses 10 thermoelectric modules to generate sufficient microwatts for its functioning. A thermo-energy harvester of 0.5 cm 2 in area by 16 mm thickness with by 2 T3 generates 10 micro-A at 3V with 5 Celsius temperature difference. An airplane engine has typical temperatures of around 100 Celsius to 2000 C. When the engine is functioning, all the energy is wasted in the form of heat. When a thermoelectric generator is implemented in airplane engine, wasted heat is converted into electrical energy. Chapter 7. Piezoelectric energy generators, PEGs. Piezoelectric energy generators convert mechanical energy into electrical energy. Piezoelectric energy generators, PEGs, are simple in structure and design, consisting of piezoelectric ceramics, lead zirconate titanate or PZT, and electrodes. The simplicity in their design helps them to fit in any small devices for power generation. A detailed study on stacks, beams and circular plates is carried in this chapter. Lead zirconate titanate or PZT is used as piezoelectric material for energy generation in the following discussion throughout this chapter. A lot research is carried on PEGs based on various conditions. The performance of PEGs is lowered when impact and resonance are applied on the PEG system. Another area of research is to control noise using acoustic isolator, which used two diaphragms. One generates energy while the other controls the noises using energy from other diaphragm. 29. Another area of research is the generation of energy from human motion using polymer piezoelectric materials and thunder actuators. 28. The basic theory used in piezoelectric effect is Young's constant. Young's constant measures the ratio between stress and strain of the particular element. An electric potential Louis is observed as the piezoelectric element is vibrated. Energy generated by piezoelectric element, E, equals piezoelectric coefficient, UI. The conversion units from mechanical vibrations to electrical energy is shown below. E equals UI equals, energy is measured in joules equals Newton meter, power from piezoelectric element equals. The numerical relation between electric field and stress is given by A equals Gs, Xi, G equals piezoelectric constant, Xi equals thickness direction axis. 7.1 Basic configurations of piezoelectric material. The basic configurations of the piezoelectric energy generators, PEGs, taken from many of the existing actuator designs are helpful in explaining the working functions of mathematical models, also helpful in separating different design concepts. Initially, basic configurations of the piezoelectric material are studied. 7.1.1 Charge generation. In order to shift the free electrons available in the coil around a fixed magnetic rotator, electromagnetic force is applied using electromagnetic generators. Whereas a piezoelectric ceramic used as piezoelectric material is a non-conductive material, so free electrons are not available in the coil, avoiding the free movement of electrons. The crystal nature of the PZT has some fixed electrons. When external pressure is applied on the crystal, the deformation of the crystal causes slight movement of the fixed electrons, generates electric force affecting the equilibrium of the conductive material. The open circuit charge generation relation is given by D equals Dijkslk. D equals constant when static load is applied, D equals charge per area, S equals applied stress, I and J equals both range from 1 to 6, 7.1.2. Dielectric properties. Dielectric properties are observed on the piezoelectric ceramics 27. A charged dipole is created when the positively charged atoms moves away from the center of the crystal. The direction of movement of these atoms from the center determines the poling direction, which can be altered by changing the heat and voltage values. Overheating of the piezoelectric ceramic results in a new poling direction affecting its polarity. This can be observed along the applied voltage seen in Figure 21. The threshold in the heating is measured using Curie temperature. The input and output relations are affected by the poling direction. Both 6 mm and 4 mm ceramic crystals are considered to be as common piezoelectric materials with 5 constants: D31, D32, D33, D15, D24. When we consider a 4 mm crystal, D31 equals D32 and D15 equals D24, D33 equals 2D31, D15 equals 5D31. Therefore the overall magnitude relations of other three constants is given by D15, D33, D31. 7.1.3. Stacked piezoelectric device. Several individual plates are stacked to form a multi-layered D33 device in order to combine the effects of individual plates. Whereas single-layered piezoelectric material doesn't support effectively for actuator purpose. Stacked piezoelectric device produce the same strain as single-plate device with low electric field. Stacked piezoelectric devices currently available are D33 devices, which are stack actuators and interdigital actuators. With this concept, the performance can be increased by n times where the total number of layers. The main disadvantage of stacked piezoelectric device is power can be generated only when the force is applied in the longitudinal direction as shown in the figure 24i. It cannot generate electrical energy with lateral force. In order to convert lateral forces to longitudinal forces, an external system for conversion is required, which in turn makes the system complex. Another disadvantage of the device is the size of the device is relatively large. The small size stacked devices are hard to manufacture. 7.1.4. Slice stack piezoelectric device type 33. Stacked piezoelectric material is broken with an external twisting force to form and slice stacked piezoelectric material. This type is advantageous when used with end bender, but long plate or beam cannot be made due to brittleness of the piezoelectric layer. One disadvantage of this device is sliced plate is only used for rectangular patch on cantilever bender, but it is not applicable for diaphragm applications. This problem can be solved by using a piezoelectric plate with interdigitated electrodes. 7.1.5. Interdigitated piezoelectric device. Interdigitated piezoelectric devices technology is evolving newly to increase the performance just by changing the poling direction. This type devices use the concept of polarization of the piezoelectric material. Below figure 26 show the interdigitated configuration. Poling direction is parallel to the stress direction and electrodes cover only a portion of the surface. Mostly the poling direction is done perpendicular to the stacked piezoelectric plate surface. Figure 27 explains the fabrication process of interdigitated piezoelectric patch. The initial electrodes present on the stacked piezoelectric plate are removed and rearranged in interdigitated pattern on surface. After this step, maintaining constant high temperatures, a high voltage is applied. Make sure that the temperatures should be above Curie temperature. With this process, poling direction is changed according to electric field conditions. The main disadvantage of this device is because of the non-uniform polling field directions and incomplete depth of polling field. Exact 33 polling direction cannot be achieved. 27. Another disadvantage is 33 polling doesn't exit exactly beneath the electrodes, also generated power less. This problem can be solved by surface electrode effect with very thin electrodes. 7.1.6 Surface electrode effect. In this concept, the PZT devices are covered with electrodes to generate different electrical energy characteristics and collect the electrical energy generated when stress is applied. This concept has its application in cantilever and diaphragm bending structures. This effect is observed in Figure 28 below. From the above figure we can clearly observe that when a force is applied in the upward direction, the inner region expands in the upper surface and the outer region is compressed in the upper surface. When the stress is distributed, the power generation will be small, because the fully covered electrodes on the surface acts as external electric field, reduce the system stiffness. In order to overcome this problem, electrodes present on the surface of the different stressed regions should be disconnected. 7.2 Modeling of piezoelectric energy generators, PEGs. In this chapter, a detailed study is carried on various electric power generation models and their equations. Below Figure 29 shows various methods of PEGs branched together. While selecting the material for PEGs, the relation between stress, strain, electric field and charge are calculating with specified equations considering the effect of strong electromechanical coupling. The power generation equation of a piezoelectric material is divided into two parts. First part is elastic energy and second part is electric energy. This is shown in the equation given below. Energy equals stress strain plus charge electric field. 7.2.1 Cantilever beam. Cantilever beam is a commonly available piezoelectric generator. Multi-layered stacked cantilever beams are widely used for mechanical bending of materials. The distribution of the applied stress is constant throughout the material when we consider the concept of cantilever. In the cantilever beam model, stress is applied only in the longitudinal direction. The charge calculation is done by differentiating the total structure energy with respect to voltage. The energy generation for unimorph cantilever beam is clearly studied by Smith JG30. By observing the above Figure 30, a force Φ is applied at the edge of the cantilever beam. This force bends the beam longitudinally. Now we calculate the momentum of the material. M x1 equals Φ Lx1. The strain of the beam is calculated with the equation given below. x1 z equals x1 m e3, where r x1 m e3 equals radius of the curvature. x1 m e3 equals curvature. The momentum of the material should be same throughout the beam. Momentum of the cantilever is calculated as m equals s e x1 z e3 z dz. The applied stress inside the piezoelectric layers is coupled with strain and electric field. Now the momentum equation is a function of curvature and electric field. M equals s x1 m e3 z dz. By calculating the above two equations, the curvature equation is obtained in terms of electric field and force. x1 Φ F3 equals F1 x1 Φ plus F2 x1 E3. Taking all these equations into consideration, total charge generated can be calculated by differentiating with respect to voltage. 7.2.2 Cantilever bender. Cantilever benders are considered as better energy generation devices because the conversion of applied force to high stress is easily done. Cantilever benders are able to generate significant deflection. They are found in applications such as microvalves. The working mechanism of cantilever bender is not complex. They are easy to fabricate. When a force is applied, one layer is in tension and the other layer is in compression. Cantilever benders are classified into types: unimorph cantilever bender, interdigitated unimorph cantilever bender, triple morph cantilever bender, interdigitated triple morph cantilever bender. Unimorph cantilever bender. When there is a change in the applied temperature in the unimorph cantilever bender, piezoelectric layer expands or contracts while the non-piezoelectric layer doesn't have any change. Neutral surface can be calculated using the following equation, where A equals cross-sectional area of each layer, H equals thickness of each layer, E equals Young's moduli of each layer, Z equals distance from the center. Subscripts 1 and 2 show upper and lower layer, P shows piezoelectric parameters, M shows non-piezoelectric parameters. Using the equation of the neutral surface strain can be calculated in terms of curvature, E1 equals ZZC/RE. ZZC, mostly used anamorph cantilever bender, is type 31. It is made up of a piezoelectric layer operated in mode 31. The electric field direction of type 31 anamorph cantilever bender is shown figure 32. Electric field in the anamorph cantilever bender is calculated by using the following principle. Electric field, E, equals voltage across electrode, V/PZT thickness between electrode, E. Interdigitated anamorph cantilever bender. Interdigitated anamorph cantilever bender varies slightly with type 31 anamorph cantilever beam at the areas with no electrodes. Basic model of interdigitated anamorph cantilever bender is shown in the figure 33 below. A. Side view. B. Top view. For a piezoelectric layer there is a change in pulling direction, but for non-piezoelectric layer the relation between both stress and strain is same as for 31 type. With the change in the pulling direction the elastic properties also change. As a result the neutral surface also changes. The overall energy of the interdigitated system is calculated by summing each segment between electrodes. E. Triple morph cantilever bender. Triple morph cantilever bender consists of 3 layers. Outermost 2 layers are piezoelectric layers and the middle layer is non-piezoelectric layer. Due to this arrangement the polarities of the 2 layers are in opposite direction. Due to symmetric nature along the cross-section their neutral surface lies in the middle of the beam. Using this basic concept type 31 triple morph cantilever bender is designed. In type 31 bender the top and bottom piezoelectric layers are connected to electric fields, I. E lower piezoelectric layer is connected to positive terminal and top layer is connected to negative terminal. Overall energy generated by this device is calculated by summing the 3 layers. The total energy generated from the force flow is calculated using the following equation, where U equals position of the layer, upper whoop, middle lower U low, VGN equals generated voltage, QGN equals generated charge from the applied force. If interdigitated triple morph cantilever bender. Interdigitated triple morph cantilever bender consists of 3 layers. The top and bottom layers are piezoelectric and the middle layer is non-piezoelectric. The polarities of both the top and bottom layers are in opposite direction. An interdigitated triple morph cantilever bender the piezoelectric material is pulled in type 33 direction. The basic view of the polarities of interdigitated triple layered peg is shown in the figure below, negative polarity, positive polarity. By observing the above figures the bottom layer should be connected to positive electric field to obtain the positive polarity and vice versa. The total energy generated from the applied force flow can be calculated as, where U equals position of the layer, upper whoop, middle lower U low, VGN equals generated voltage, QGN equals generated charge from the applied force. 7.2.3. Diaphragm with constant pressure. Diaphragm structure is same as circular plate structure, commonly used to detect acoustic pressure and hydraulic pressure. The elasticity of the thick plate shows that there is no stress and strain along the thickness direction. Also the deflection generated is much smaller than the thickness of the plate. When a constant pressure is applied to the diaphragm, we get 2 moment terms. One term is in radial direction and the other term is in angular direction. As a result there will be 2 curvatures each in the form of moment terms. The elastic properties are same for both moment terms. 3 types of cases are considered in diaphragm with constant pressure. Anamorph diaphragm, anamorph interdigitated diaphragm, triple layer diaphragm. I. Anamorph diaphragm. In the anamorph diaphragm the neutral surface is not located in the middle of the surface because due to change in the electric field neutral surface moves from its position. In order to calculate the neutral surface the elastic properties of PZT material are taken into account. A schematic view of the anamorph PZT diaphragm is shown in the figure 35 below. An example of this type is type 31 anamorph diaphragm. In this type of diaphragm the electric field is constant throughout the structure. The strain curvature of the type 31 diaphragm can be calculated using the following equation: R equals R ZZC E equals ZZC E. Unimorph interdigitated diaphragm. In unimorph interdigitated diaphragm, overall energy generated can be attained by integrating over the volume where no electrodes are present on the surface. For the pulling process to occur, the electrode's position should be far and narrow from each other. A schematic view of the unimorph interdigitated diaphragm shown in the figure 36 below. By observing the above diagram, there are a number of clusters with n+1 number of electrodes located on the surface. A is the radius of the diaphragm and B is the width of the electrode. The total energy generated after an external pressure is applied is calculated by using the following equation: UGN equals QG and VGN. E. Triple layer diaphragm. The electric field direction of PZT layers has opposite polarities. It consists of 3 layers. In a triple layer diaphragm, the top piezoelectric layer is connected to negative electric field and bottom layer is connected to positive electric field. An example of this type is type 31 triple morph circular plate. In this type of diaphragm, the total energy generated with the application of constant pressure is 0. Chapter 8 Model Preparation. Various steps are carried out while the specimen preparation. Aluminium substrate and a PZT layer is used while preparing a unimorph diaphragm. A PZT layer of thickness 0.127 mm is used. The fabrication of the model is done in different steps like etching the PZT electrodes, pulling and bonding. The etching process is carried mainly to modify the pulling direction in certain areas. In order to etch nickel electrode, ferric chloride acid is used, and for masking, acid-resistive ink is used. The pulling process is done at high temperature and high electric field as discussed earlier in the chapter 7. The Curie temperature should be 250 C, with electric fields of up to 2000 volts per millimeter. After finishing the process of pulling, it is tested for pulling direction with the help of PZT transformer, phase test. Conclusion: in the recent years, a vast area of research and investigation is continuously carrying on a number of ways to extract energy from environment and surrounding activities and convert it into electrical energy to power low-power electronic devices. Researchers have shown that harvesting energy from day-to-day activities plays an important role in developing future microelectronic devices. Evolution in the technology of batteries and reduced power consumption has closed gap between generated energy and energy spent. Recent developments in nanotechnology, microelectronics and communication techniques add to reduced power consumption. This paper has provided a review on state-of-art energy harvesting technologies to power low-power electronics. This paper also discusses various types of energy harvesting systems, their architecture, types of energy sources available, battery technology, power consumption. Practical implementation of power harvesting technologies and advancement in low-power electronic reduces the emission of greenhouse gases to some extent. 7. Risk assessment. Risk assessment table shows the risks which are likely to come in the course of project, which is evaluated for the factors like importance of the risk and likelihood to happen. Risk, LO, M medium and H high. Importance likelihood 1. Hardware crashes HL2. Poor system performance HM3. Software unavailable HM4. Software license ends LL5. Software doesn't work H86. Supervisor leaves L87. Personal reasons like illness HM. 8. Risk management. The risk management evaluates the consequences and the control measures to overcome the risks presented in the risk assessment table. 1. Entire system fails, use another hardware. 2. The preceding system will not work, improve the system performance using proper implementation. 3. The system can't be implemented, try to get the software working, use another software. Worst case. 4. Cannot use the software by the license. 5. The user interface will not work, correct implementation of the software. 6. Lack of experienced person to evaluate. Seek the help of other experienced guy, follow the supervisor. Worst case. 7. Cannot continue the work, try to work if possible, apply extension for submission. Worst. 9. Professional, legal, ethical and social issues. Professionalism and avoiding plagiarism as key factors in every research project must be considered, but in this project there are no professional, ethical or social issues. Please be aware that the free essay that you were just reading was not written by us. This essay, and all of the others available to view on the website, were provided to us by students in exchange for services that we offer. This relationship helps our students to get an even better deal while also contributing to the biggest free essay resource in the UK. Thank you for taking your time to listen to me. I hope you enjoyed learning about developing embedded electronic technology as much as I did. Kindly remember that you can get a custom, plagiarism-free essay at EssayKnights for as little as $10. The link is in the description. See you next time.